Hi everyone, my name is Nicole Gugliucci. I am at dotAstronomy in Germany, so this is the first time I'm broadcasting live from another country, and so I apologize if there's a lag or a funky video and whatnot. So I'm at a conference called dotAstronomy, and with...
My name is Demitri Muna. I'm a astrophysicist who works at New York University.
Okay, so what kind of work do you do at NYU?
I work on a project called the Sloan Digital Sky Survey, SDSS, and this is a survey that is currently cataloging, something like 1 million galaxies and even more stars, and getting Spectra. Not to get too technical, but
no, that's fine.
Okay.
Hang on a sec. While you are describing that, I'm going to make sure we bring up the comments. I didn't bring any of my fancy things. So I apologize if this is a bit more ad hoc than our recordings usually are. But I want to make sure I can see everyone's comments as well.
Well, this is like live in the field, so.
Can't even watch from Germany. Okay. Yes, this is live in the field. I didn't bring my nice microphone or camera or apparently the correct internet at all. Okay, so you work at NYU. Working on it, SDSS, which is more jargon, Sloan Digital Sky Survey.
Sloan Digital Sky Survey, yes.
And what are you doing here at dotAstronomy?
So dotAstronomy is a conference/workshop sort of thing that seems to take some of the latest technologies like CSS and HTML and crowdsourcing and cloud computing, that sort of thing, and trying to merge that with the astronomical community, which doesn't necessarily embrace like the latest technologies, and to say the least.
Which might be a surprise, because you think scientists, computer people, very ahead of the game on top of technology. But in some ways we are. We use like the cutting edge technology and detectors and equipment and things like that. But as far as programming languages and social media tools and things like that, people kind of get set in their ways. They've learned the one thing that they've learned, and they don't tend to move on to something more modern. So this is one of the things that this conference is, I think, helping with, is trying to expose people and encourage that kind of use. Okay, what kind of projects? Like, for example, today was what we call Hack Day.
Right.
We're all working on different projects, things that we've come up with while we're here at the meeting together. So what kind of things are you working on today?
A couple of the projects had similar themes. Like a couple of them was about just connecting astronomers. So there might be an astronomer who is familiar with, has some skill or some knowledge or something, but having someone else find that person to help them to do what they need to do, there isn't any kind of real central kind of exchange of how to exchange skills and things like that. So there are a couple of projects that I like that. Another one that I'm working on is if, let's say I have a particular skill and I happen to be traveling to some place, and there's a planetarium somewhere and they need somebody to give a talk to children or something like that. So I would list like my skills, like maybe I can speak to children about astronomy, and then I would just post that and then post where I'm going to be. And then somebody who needs that skill might say, I'm looking for somebody who can do this, and then there's a way to connect people like that.
And so that's matching up the time and place.
That's right.
Astronomers travel so much.
Yes, and that's one of the things, is that astronomers do travel quite a lot to conferences and observing things like that. So the likelihood of like an astronomer crossing your path, through town is not too bad. Okay,
cool. Yeah, some other things I've seen people doing today are ways of linking up. Taking out the specific words out of a scientific paper or the abstract of a paper and trying to see what topics correlate with each other.
Right.
We have a couple of video projects in the works. Yeah, all kinds of cool stuff. So then how would you say that dotAstronomy is different from a typical science conference?
Most science conferences have a set agenda, and you go in, at 8 or 9 in the morning, and there are scheduled speakers and scheduled talks and things like that, and they go through most of the day with your obligatory coffee breaks in between. And this conference started out the same way. We had a couple of invited speakers, and they gave their talks, and then people went to a whiteboard and wrote down things that they wanted to talk about, and just, the ideas that just kind of triggered, by coming here, the things that interest them in particular. And then people would tick next to each one of the topics what they were interested in attending. And then for a lot of the day, it was just spent, okay, go into the different groups, there were like 3 or 4 different rooms, and then we'd talk about, the topic that people just came up with, the day of. And that's interesting because a lot of the times in these conferences, when you get people together, they start talking during the coffee breaks, and people start going off on a tangent, and then the coffee break's over in 10 minutes, and then we go back to their regularly scheduled talk. And this is like the inverse of that, where there are a couple of talks, but mostly it's find a tangent and just really explore it and do that. So it's an interesting exchange of ideas.
So Cook Station ID, we're talking about dotAstronomy, which is the conference that we're both currently at Heidelberg, Germany. So it's kind of at like the unconference model.
Yes, that word has been thrown around a lot. So
I've heard that. Yes. Is this your first dotAstronomy?
This is my first dotAstronomy.
Oh, me too. Okay.
I'd only discovered it after the last one had come about, so it's definitely something that I would have been interested in before.
So are you looking forward to continuing the projects that you're working on after we all leave Heidelberg?
I think so. I have to put a caveat on that, not because of the quality of the projects at all, because I have so many of my own personal projects on the side that diversifying even further isn't necessarily the best use of my time. But helping out is something that I'm always happy to do. So
good. I'm going to ask if anyone has any questions. Sadly, this broadcast seems to not be available in Germany, which is where we are, which is unfortunate.
Except for us, because being in Germany is pretty great right now.
Yes, we're totally doing it, doing the internet thing. So, but if you have any questions, please leave a question in the comments, and I will try and pick up on that, hopefully without crashing my laptop by doing anything. Hi, Beth. Okay. Can you tell us a little bit more about your science that you work on?
There's
for a general audience.
For a general audience, there are a couple of things that I have my hands in, so to speak. So we get in our telescope, we measure what are called spectra. So to kind of briefly explain what that is, so you're familiar with a prism, and you see light, kind of the rainbow of light breaking out of the prism. So if you just have white light, you just see a clean rainbow, and everybody's kind of familiar with that. So let's say instead of let's say you had a flame and it was burning magnesium, for example, some element. What you would see in that rainbow. So you see this
there we go.
band of light. So let's say you were burning magnesium. So instead of this rainbow of light, you would see this rainbow, but there would be a couple of dark lines. And those dark lines would be very characteristic, will be specifically characteristic to the element that's being burned. So just by seeing those dark lines, you can say, oh, there's magnesium that's coming from that light source. So that's a signature of that element. So every element has its own signature. So if you see a spectrum from a star, if you break the light from a single star, you'll see a whole bunch of different lines, and that'll tell you what's in the star. Basically.
So it's like chemical analysis using you're not actually sampling the star, but you're just using the light from the star to analyze what it's made of.
Exactly. And you can do that with a galaxy too. And that's one of the really interesting things, is that I can see a galaxy that's, huge distance away, and I can tell you there's oxygen there, there's nitrogen there, there's carbon, there's whatever. But more than that, just because based on the shape of the information that comes from this spectrum, I can tell you that this is an early type galaxy that might be creating a lot of stars.
What does early type mean?
So basically,
there's a history there.
Did I just get technical?
No.
Welcome, viewer.
Welcome back, viewer. Okay, so yeah, we lost our feed, so we're not going to do too much longer. Maybe I can cut these back together, but I don't know at what point we dropped out, but we were talking about spectra and early type galaxies, which really means...
So, yeah, the morphology of,
So it's round.
It's round.
It's round, it's not spiral.
Right. So what I had actually meant was, a galaxy goes, ages just like everything and evolves just like everything else. And so when a galaxy is early in its life, it's forming a lot of stars, so you see a lot of activity, and so the spectrum that you see is characteristic from that activity. And what happens is that you've got stars that are very young, but you also have very large stars, and large stars burn very bright and very fast. So when a galaxy is just first forming a lot of stars, basically the light you're seeing is coming from these very few but very large and hot stars. And then contrast that to a much older galaxy. Those stars that are very large, they've burned out, and what's left are kind of like stars like our own sun. And so you'll see a different shape of the spectrum that comes from the galaxy from these things. So the idea is that you can look at these spectra and you can deduce a lot of information, not just like what material is burning in the galaxy and the stars, but its history as well.
Right, right. Yeah, because, I mean, all the galaxies except for our nearest major spiral, Andromeda, you can't actually see the individual stars, and so you have to rely on the spectrum of the entire galaxy itself to infer the properties of the stars within it.
Exactly. And one of the nice things about the BOSS survey, which is one of the sub-surveys in the Long Digital Sky Survey, is that I think we're up to something like 2/3 of a million spectra.
Okay.
It's a lot of spectra. It's a crazy amount of spectra, but that's the great thing about this, is that you can take and these large amounts of spectra and do statistics on them. And even though we can't get the signal to noise on each individual galaxy is not too terribly high, what you can do is select spectra that are very similar, like even hundreds and hundreds of spectra that are similar, and do what's called stacking them. And basically you add them together, and what happens is the signal to noise gets much higher. And so you can actually see, like, for every wiggle and every bump on that line, that's a feature that is science. Like, that tells you something. Instead of noise, it's like those are individual features. And you can really compare models that you have that describe how galaxies evolve, to within these individual features.
Yeah.
And it's really amazing.
And that the fact that there, would you say 2/3 of a million?
So far. And counting.
That brings us back around to one of the reasons that we have dotAstronomy, is that the size of the data sets in astronomy are getting so much larger. They're terabytes and terabytes of data.
Right.
So we need to become more computer savvy, I think, is the message we've been hearing.
That's a lot.
Deal with it.
Yes, I think that's right. That's certainly a drum I've been banging for a while.
Yes. Yes.
But that's the thing, is that we're going to have so much more data. It's not something that's growing in a small amount. It's growing very quickly.
Right.
And
it's just kind of like...
Yeah, exactly. And as astronomers, I mean, a lot of astronomers don't have a lot of training in just dealing with computers and programming and things like that, and databases and whatnot. But this is, one of the things that we've been talking about at this conference, is that, we're going to have to learn as a community how to deal with data sets that are that big, that don't fit on, that cannot fit on your laptop.
Right.
And that you have to start using, like cloud services or something like that to process and to analyze the data.
Yeah, yeah. Cool. So. All right, I think we're going to wrap up before we lose the internet again. I'm going to do a quick refresh, see if there are any burning questions. But since we lost the stream and we may lose it again, I think we're going to wrap up with that. Hang on, let me refresh really quickly. Thank you for coming in and coming back and bearing with us. Here's a question. How can we determine the quantity of elements from their spectra? Is there a way to determine quantity? That's a tough question.
Yeah. It's not really quantity that we're looking at. What we do is we look for the relative amounts of one element to another.
Right.
So I can't say that this galaxy has this many pounds of gold in it, for example. That's not gold. That's the rich galaxy.
Yeah. It's mostly hydrogen and helium. We know that much.
Yes.
But as far as actual abundances, it's a
actual mass amounts is not something that we're even interested in. I mean, that's not what we're looking for. But by looking at the different relative amounts, like saying, this much carbon versus this much oxygen, that can tell us about some processes that are going on in the galaxy.
Right.
So that's one of the things that we look for.
Cool. And thank you for the question. Maybe we won't lose. Right, relative amounts. Okay, so great.
Oh, so right. So the way we do that is just by the strengths of the line. So you might see, so I talked about in the beginning, hopefully it wasn't cut off at this point, that you might see dark lines like in a rainbow, but what an actual spectrum looks like, and it's basically the same thing, it's basically like a squiggly line.
Right, because you turn that one-dimensional thing into a two-dimensional plot.
That's right.
Yeah.
That's right.
That's how we tend to look at it.
Yeah.
As astronomers.
And so, like, this one bump might be oxygen, and it'll have a certain height on this plot, and then you might compare it to something like carbon, and it'll have a different height. And so by comparing those two heights, you compare the relative distances.
Right. Cool. All right. Well, cool. This is Nicole and Demitri live from dotAstronomy in Heidelberg, Germany, where we are doing astronomy and computing and outreach and all kinds of crazy things.
And hacking today.
Hacking, lots of hacking. Making the world a better place through hacking and astronomy. Thank you.
Thank you very much.
Thanks for watching.